right, welcome everyone. Thank you for joining us. As Pragati said, thank you for joining us so early, well, at least early for some of us, pretty late for some of you. My name is Michael Johnson. I am a I own a little consulting company out down in South Africa, and I'm also a data platform MVP. And today I'm going to be speaking to you about diving into Deltalake. So Deltalake is this new storage layer that's quickly becoming the sort of go-to platform for a lot of the big data initiatives that we're seeing, particularly in the Microsoft and Databricks worlds. Some of the other guys have other similar sort of products, but yeah. So we're just going to walk you through sort of what that is. Okay, so just a little bit of agenda. We're going to have a look at what is Deltalake. We're going to have a look at how it works, and that's where we're going to spend the most of the time is really, looking at how those inner bits work. And also, Deltalake is obviously a big topic, so we're going to have a look at the sort of foundational items. So we're not going to look at some of the newer stuff, sort of deletion vectors and all those kind of things. These are strictly the sort of, those sort of early versions of Delta. Then we're going to have a look at how you can use it, and then we're going to see that you've actually got to maintain it. So it's a little bit like a database in that way, right? We've got to run those sort of maintenance jobs. Then we're going to wrap up by looking, should you consider it? Why would you not want to consider it? There we go. So what is Deltalake? And the best place to sort of start with that question is usually their website. And they have this nice little blurb, which I won't sort of read out to you. But there's a couple of things that are important. The first thing is this idea of it being open source. Now, it's not open source in the strict sense, because it's actually an open format, or an open protocol, not so much the actual source code. If you go to their website, so you can see in the bottom there, they've got delta.io. They have a link to a GitHub repository, which has a reference architecture for Deltalake. And also, it was built by the people who gave us Spark and ultimately started the Databricks sort of organization. So they have their own implementations. They have implemented a Spark specific version. So if you want to see how they did that, Spark is all open source. So you can go check out how they've implemented it, but you can use it in other mechanisms. All right. The next thing is built for a lakehouse architecture, right? So we're going to see that we can do a lot of database-like operations, right? So we're going to be able to insert data, delete data, select, all of those things we're used to something in a database, but this is really not for OLTP or transactional systems, right? It's a little bit slow for those very small transactions. This is for working with large sets of data. Now, in the demo, we're not going to be looking with large sets of data because we want to kind of see how all of those individual atomic operations happen. But ideally, it is for big pieces of data. And then finally, as I mentioned earlier, it has a lot of implementations or compute engines. Okay, so the big one was obviously Spark. But there's obviously PrestoDB, Fink, Trino, Hive, and then you get standalone versions, right? So if you just want to use it on your local desktop, you absolutely can use Python, Scala, Java, or Rust. Okay, so that sort of speaks to what Deltalake is from a sort of little bit of a definition. But let's go and have a look at, why would we consider Deltalake, or what is the problem it's trying to solve? And switch that slide there. Okay, so why Deltalake? And there's sort of two competing ideas behind how we work with data up in the cloud. The first is to use a file, right? So just a standard file, usually CSVs or JSON files or some sort of binary format. And then more recently, we've seen column store files come out. So we've seen Parquet and Avro, those kind of files. On the other side, we had databases, usually a relational database, but not always a relational database. There are other types of databases. And these gave us a lot more functionality, but they had other limitations. So let's just have a look at three that probably sort of help us position Deltalake. Okay, so the first one is cheap. So we're not speaking strictly about cost, or at least the implementation cost, but that whole cost, right? So there's the cost of compute, there's the cost of the storage, there's the cost of maintenance, all of these kind of things. And files have always been very cheap to maintain. Okay, we can sort of create a little data lake up in the cloud if we want to call. Data lake is obviously a very loose-fitting term. It's the governance that really make it a valid lake. But we can create the storage structure in the sky and we can start uploading files, and that's very cheap. Databases, however, are a little bit trickier. We have to pay for that sort of compute. We often have to pay a licensing fee. They also often a little bit, we don't get to create them as easily. Okay. Then there's compute bound, right? And this is where we speak about databases. Now, databases have to have a running engine attached to them. So we can't just randomly sort of start querying it. Now, there are modern architectures for databases, SQL Server serverless, but those are sort of maybe more abstractions over more than the actual intent behind it. But the point is you still have to go through some sort of engine that actually provides that interface to the files as opposed from working with them directly. And then finally, we get this idea of transactionally safe. Now, there's a better word for transactionally safe, and we'll get to that in just a second. But the big thing we want to look at is, what can they give us? And files give us no transactional safety, right? There is nothing that stops conflicts from happening when we try to do all of these sort of operations that result in all of these little conflicts. All right, and databases do, and they do that using locks. Okay, all right, again, so we're just going to go through an example of how a file does not provide any transactional safety. Now, I've got a simple file over here. It's a simple data set, and we'll call this data set A. And then we have two actors. So we have Alice and we have Bob, stolen from the sort of security world. Okay, and Alice and Bob want to make a change. So Alice would like to add, make her amendment B, whatever that is, and Bob would like to make amendment C. Okay, so they're both going to go and make a copy. So Alice is going to grab a copy and Bob's going to grab a copy. So they've both got isolated copies right now in their own sort of environments. And they're going to go away and they're going to do these modifications. So Alice adds her modification B and Bob adds his modification C. Okay, so all's good now. Now we need to write that back. So the way we do when we're modifying things in files, essentially what we have to do is we have to delete the old version and then replace it with a new one, right? Okay, unless you're working with a strictly append-only process, where we're only ever adding data. It's a typical IoT scenario. But if we need to run things like updates, this is where we get that sort of problem. Okay, so Bob's going to take his change set and he's going to go and delete the original version up in the cloud. And he's going to then go and replace it with his version, so AC. And Bob's now finished. So he knows that he's committed in his transaction and all his work is safe. And then Bob can now leave. Okay, now Alice obviously hasn't committed yet. So she's going to do exactly the same thing. She's going to go and target that data set. But it's kind of different from what she had. But she doesn't really know that because there is no way for her to know that. She's going to go and delete change set AC, going to replace it with AB, and she's going to be happy, right? So both of these people think that they have committed their work successfully. However, Bob, hopefully he's going to know about it, but there's actually no way, there's no feedback mechanism for Bob to know that his transaction was no longer valid. Okay, now we spoke about there being a fancier word for this, really, and that is ACID, okay? So ACID comes from the sort of database world, and we speak about 4 properties that we want in a data store, okay? Now, they are atomicity. So atomicity means that the whole transaction goes through or none of the transaction goes through. So we don't get partial transactions. So if you can imagine that we were working on a, let's say an account table where we were doing some transaction and we were doing some sort of logging, we want to make sure that if we modify the transaction table and then we insert a record into the audit table, we want to make sure that both of those transactions go through or none of them do, because the last thing we want is one of those transactions to go through and the other one doesn't. Maybe a more practical example is if you went and bought something through an online store, the last thing you'd want is for your account to be debited, but the product not to have actually been put in the, set for shipping, right? Okay, so that's atomicity. Then there's consistency. So consistency really speaks about that ability to make sure that all the rules around the model are kept intact, right? So any sort of primary keys, foreign keys, sort of any sort of constraints that you have in your database, we make sure that all of those things are being applied. Okay, less or almost not entirely relevant to databases at all because there is no schema. All right. Then there's isolation. So isolation is that we guarantee that any work that we do can't be interfered with by somebody else. So if 2 people are doing work at the same time, those two operations can't interfere with one another. And the way relational databases deal with that is by taking locks, and we'll discuss locks in a second. But this prevents different people from working on the same objects at the same time in a destructive way. Okay. And then finally, there's durable. And this really speaks to that point that we saw earlier with Bob, is that when I get a confirmation from the storage layer that says my transaction is complete, I should be able to leave knowing that that is the case and that there's nothing that's going to sort of prevent that. If we think back to the SQL world, we've got SQL tables, but we also have the transaction log. So even if something happened to the SQL tables, we have this log that can essentially recover all of those things. So even if the database crashed immediately after I'd committed that transaction, before everything was written down, I know that there is a mechanism such that that would be recovered. And text files largely have none of this, okay? Databases do, but databases come with that cost, okay? And when we're dealing with sort of, terabyte, petabyte size tables, building a relational engine over those kind of data stores becomes very expensive. Okay, so how do we do ACID, right? And there's really two ways of doing it. So we spoke about the first one. We didn't call it that, but it's pessimistic concurrency. So pessimistic concurrency is really about the database begins by assuming that there's going to be conflict in what it's going to do. So it assumes that there's two actors who are going to come in and try to make modifications to this thing. So it takes a thing called a lock. Okay, so a lock essentially says, nobody else can modify this object. Now, in different database types, there's different types of locks. So in SQL, we get read locks, write locks, we get shared locks, we get lock escalation, all of these different types of locks, but it becomes pretty complex, right? And then the other version, as you might guess, if it's the opposite of pessimistic, is optimistic concurrency. So optimistic concurrency says that I'm assuming there's not going to be a violation. What I'm going to do is I'm going to do my bit of work, and then I'm going to check if that caused a problem or not. Okay, so yeah, optimistic works very nicely when the chance of conflict is low. Obviously, pessimistic works in a high when there's a high chance. Okay, and there's a balance, and Delta actually prefers the optimistic concurrency because specifically in a analytical platform, there's not often that many conflicting transactions. In fact, most of data warehousing is really around appending data, which is a completely a safe transaction, right? But there can be other things we do. We can change a schema, we can delete data, we can modify it, we could roll it back, we could do all of these kind of operations that we might want to perform on our data. Okay, so back to this idea of what is Deltalake. Okay, Deltalake at a very abstract level is actually just a folder, okay? And it has two types of files in it, okay? It has data files, and data files use Parquet. Now, in the protocol, there is support for something other than Parquet. It's not necessarily defined. I've only ever seen Parquet used. Now, Parquet is again, it's another open source format, open sourced using the same licensing model as Databricks. So this is all under the Apache Foundation. And Parquet gives us essentially what is called a column store database. Okay, so everything is stored in columns, and then we get great compression out of it. Very similar to what things like Power BI and column store compression use, right? Okay, so we've got these little Parquet files, and we just store a whole bunch of them. So there's the data files, and then there's this idea of a delta log. Okay, so the delta log is made up of a whole bunch of JSON files. Okay, and every time we perform a transaction, we create one JSON file. Now, so you can see that there is essentially a sequence, right? So there's a log sequence number, so you can see it starts at 0, 1, 2, 3, 4. But you'll see that number 10 actually has something slightly different. Okay, so that actually is it's called a checkpoint file, but it's also a Parquet file. And that's because parsing JSON files is actually really expensive. If we think, they're really quick to write because they're just little text strings, but aggregating them, now, if there's only 9 of them, probably not so expensive. But you can imagine if I've made 1 million transactions, if I had to read 1 million little JSON files to understand the state of my database, that would be sort of very prohibitive. So every 10 records, or so we can force the checkpoint a little bit earlier, we get this idea of it rolls up all of the transactions before then into that single checkpoint file. So it's a summary file. Okay, so that means that every so if we had 25 files, then we'd have, or 25 transactions, we'd have the 25, but then we'd have sort of 2 checkpoint files. And how that actually means is that in order to understand the full state of a database, all I would need to do is find the last checkpoint and then read any JSON files that have happened after that. So those are the 2 files that we need. But how do we find that last checkpoint file? And that's where that very first table that first little record that you can see, which is the last checkpoint, that's a pointer to the last checkpoint. And this file actually breaks a lot of the rules around that Delta, because everything that happens in Delta is write forward only. So we actually make no modifications to any file in a Delta file except for that last checkpoint file. Okay, so everything is write only. Okay, so that's a very simple little sort of overview of what it does. And we spoke about those 2 things. Yes.
Sorry for interrupting. So there is a question, I think it relates to what you just showed on the previous slide. So this is a question from Rizwan, and he's asking, like, how about locks in Deltalake when similar transactions are being accessed by different users?
All right, so we're going to cover that very shortly. So there's a slide coming for that. In fact, there's lots of slides.
Thank you. Okay, makes sense.
Cool. Okay, so how do we solve this problem? Okay, we use append only. So we said how we only ever write files. And this is actually what gives us, because ultimately, in order for a safe system, you actually need some level of locking. But we don't, within Delta, we don't actually use any locking. All we use is we use a guarantee by the storage system that we can only ever create a file and not overwrite a file. Okay, and that's actually provided by something like Azure Blob Storage, or your local file system can provide it. So essentially, the only guarantee we absolutely need, and there's 2 guarantees you need from the storage system, is that we can write to a file, and it will either create the file with the content that we wanted, or it will fail. Okay, so there's no overwrite. Okay, because that's exactly where Rizwan was going with that. It's like, what happens if 2 people try to write the same file at the same time? So the sort of underlying storage system prevents that. Okay, and the second one that we need to make sure is that when I query the content of a folder, it will only display the content of files that have been fully written. So there's no partial records being written there. So those are the 2 guarantees, and actually not very important to what we're doing today. But just so you understand that there is some level of locking that's been provided by the storage layer. And then there's this idea of optimistic concurrency. So we'll show you how optimistic concurrency works. Okay, so first off, we work with this idea of append only. So we've got our 2 actors, Alice and Bob again. And Alice will go and make a change. So she'll go and create JSON1. Okay, and then Bob will then, Alice will go ahead and create change set 2. And then Bob will go and create change set 3, and Alice will go and 4. So we've got that idea of always just appending these transactions, and those transactions can be anything. They can be add data, delete data, modify data, whatever those are. We'll get into those atomic operations shortly. But you can see that we're only ever appending, which is kind of weird, because even if we're deleting, we're actually appending, right? We always write more data. Okay, all right. Again. So we'd then end up with a whole bunch of data that would look something like that. We showed you that earlier with that sort of checkpoint and those JSON files and that last checkpoint pointer. So the big thing about that, using that last checkpoint, the idea is that you'd only ever have to do 11 lookups to understand the full state. You would read that last checkpoint, you would read the actual last checkpoint Parquet file, and then you would read any JSON files up until that point. And at that point, you get the full state of the table. Okay. Yep. So those are those are the 3 little files. Okay. Then we can look at optimistic concurrency. Okay. So this is how we deal with that idea of conflicts. So let's say both actors wanted to make a change. This could be Alice and Bob, and the current state of the database is version 1, right? So they're both going to make a copy of that. They don't, they read that the log chain, so they will have read up to the last. So let's just pretend it was JSON 7. They would have read all 7 items in there to understand the table. Then they would want to go and make their own changes. So they would both write to the storage mechanism, but only one of them could have succeeded. Okay, so the underlying storage system would say, you know what, Alice, you're succeeded. You both tried to create a file called 002. Alice, you got in because you were there just milliseconds before, or nanoseconds, whatever that is. And then Bob's got to fail. So the important thing is that Bob knows that his transaction failed. Now, this can seem to be very expensive because Bob now has to go and redo his transaction. But Bob can actually understand, because he now knows that Alice has written a transaction, so he knows that she wrote transaction number 2. She can go and look at what kind of transaction she wrote. And then depending on what he's going to do, he can determine if he needs to do a lot of work. So the most typical workload, as I mentioned earlier, in a sort of data lake environment is really to append data, right? So we're just adding more data. And we actually almost don't care what Alice did, okay? Because even if she deleted records, if she added whatever she did, okay, there are some transactions that don't meet this, but I can probably just append. So he's just going to go and create another record number 3. Now, the exception to if he's doing an append is he's going to have a look and see, did she change the schema? Now, that's probably the biggest risk. So he's going to determine, did transaction number 2 change the schema in some way? And then not. But if he's going to do a transaction like a delete, well, then he needs to ensure that Alice didn't maybe delete that data first, or update it, or whatever that is. So he needs to actually understand what changes Alice made to know if his transaction can just be replayed or if he's got to recalculate it. And that's where we talk about that idea of optimistic concurrency. You're actually kind of doing a whole bunch of the work and then hoping it'll stick, as opposed from locking everybody out and then knowing that you can do your work, but you're blocking them. Okay, optimistic and pessimistic concurrency, both absolutely valid in their own use cases. We're not saying that either one has a valid place in this world. Okay. All right, so now we're going to talk about using Deltalake. Oh, so Rizwan, I hope that sort of answered your question there. I see you did put a little tick there. Okay, so now we're going to have a look at how Deltalake works. And Deltalake is essentially, as an abstraction, is a storage mechanism, but it also comes with a sort of very SQL-esque like syntax. Okay, so we're going to use that sort of process. So we've got 3 little areas we're going to look at. We're going to look at the command. We're going to look at the files that get created. And then we're going to have a look at the transaction log entry. Okay, so the first thing that we're going to do, and this is something that we can't do with a CSV file at all, CSVs or Parquets or anything, is I'm actually just going to go and create a table. So I'm going to say create table product, and I'm going to give it a schema. So Parquet files have a schema for the file itself. But if I go and add a second Parquet file to that same folder, there's no sort of schema enforcement between those 2 Parquet files. But here I'm actually saying that everything that now comes into this storage layer, or the storage function, must obey this this schema. Okay, so it goes and creates a table, and this table is empty. Okay, so all of a sudden what we've got is in this file section, we have no files because there is no data, but we do get a Deltalog record. Okay, I won't show you the content of that Deltalog record, but the actual transaction is going to look like this. Okay, so it's a JSON file, and it actually has more to it than what I just showed you. But there's really 2 bits that are really important. The first bit is, what did I do? Well, I created a table, and it's a managed table. Okay, so that's sort of ready for its own internal purposes. And what managed really means is that if I delete the table, should I delete the underlying content? Okay, and then I've got this metadata. So the metadata describes what this thing looks like. So you'll notice that there is this idea of a provider being Parquet. The implication is that we should be able to use something else like Avro. I've never seen it done, but I guess that it's supported. Okay, and then we've got this schema string, which is really just the schema that we got from the create command. So we can see that we have a struct. It has fields, and one of those is a product name of type string, which aligns to my product varchar. Right, varchar is obviously a SQL-esque kind of syntax, versus string is the underlying data type, but they are the same thing. Okay, so we've now got a single record in our Delta table. We've got no data, but we have a table. Okay, so the first thing we're probably going to want to do to that is then go and add data. So add data, exactly like we get in SQL. Okay, so I'm going to go and insert 2 records. I'm going to insert an apple and a pear. Okay, so it's the product name and the product price. So we're going to go and add those 2 records, and you can see that we have essentially those 2 apple and pear in our table. And then we've got a delta So we get our first Parquet table. So this is the actual data that sits in there. Now, Parquet doesn't necessarily perform very well with 2 records at a time. So ideally, we're working with larger data sets. That's when we get the best compression, but we absolutely can support, single record upsets. Okay, and we're going to have 2 Deltalake records, right? So there's going to be 000, which was the create table, then 001, which is going to be our append. And that's going to look something like this. So again, what are we doing? Well, the commit information, the operation this time is a write. Okay, and it doesn't log what I wrote into the table. This isn't a transaction table like SQL. What it does is says that I added a Parquet file in there, right? So that is this Parquet that we've got in the file section there. So now we've added 1 Parquet file to this log chain. So when I query the state of the database, I know where I can go get the schema of this thing. And then I know exactly where I can go and get the first bit of data. Okay, first operation. Next one is we're going to do an update. So an update is we're going to go and change some records. So I'm going to go and set the price of apples to 7. Okay, and then my table is going to look like that. Now, you might be thinking to yourself, we're then going to go and access the Parquet file. We're going to read it, we're going to change it, and then we're going to overwrite it. But we saw earlier why that's a bad idea. So instead, what we're going to do is we're going to create a second file. Okay, so now we've got 2 Parquet files. Okay, we've got the first one and the second one. Just a note, don't ever think that the order of these files, these are goods, right? So don't think that they sequentially mean anything. Okay, but in our transaction file, we do 2 things. You can see that we're saying the operation here is an update, and an update is actually 2 things. It is it's removing the old file from the log chain, and then it's adding a new one. So essentially, what I'm doing is I've now got 2 Parquet files. I've got 1 Parquet file that looked like the original one, where the apple price was 5, and then I've got a brand new copy of that table where it's 3. So immediately, you can see how that works. So now I can go and get the state. When I go and query the state at state 3, I'm going to go and grab the version of the table that looks like this. But all of a sudden, I'm storing twice as much data as I should do, which for 4 records probably isn't a problem. But you can imagine that if we're working with terabytes of data, this could be a fairly expensive operation, and we'll get to that in a second, right? Okay. So we've now done that. Now we're going to bring in a delete. So we want to go and delete a record. Now, we spoke earlier about we never ever actually, we only ever write forward, we never delete. So we expect to see that exactly the same pattern. Okay, so a delete and an update are effectively pretty much the same operations. Okay, so we're going to say delete from product, where product name is Apple. My table now looks like this. It's only got a single row, but I've gone to a 3rd record. Okay, and my transaction record actually looks exactly like the update. It's just called a delete, but essentially what I'm doing is I'm removing the V2 version of my table, and I'm replacing it with the V3 version of my table. Okay, so we've now got this accumulating idea coming along. All right, so we spoke about DML operations, but we can also do DDL operations, right? So we can go and change the schema of a table. So I can do things like alter table, add a column with a quantity. So I'm going to go and add that record to my table. I've now got, you can see that I didn't pick up another table, right? So we had the 3 and we've still got 3, and that's because this is, again, it's a metadata operation. Nothing actually modifies the data in those Parquet files, and I end up with a transaction record that looks like this. So I'm going to go and say add column. The column I'm going to go and add is that quantity, and it's of type integer, and it's nullable, right? So these are all the constraints I put on my column, and then it redefines my schema. So I can say that this is now my schema from transaction record number 4 onwards. This is what my schema does. Now, if you've ever worked with Parquet files in the past, and you added a column, you'd probably know that you're actually going to have to go and open up all of your Parquet files and add this new column. But Delta actually manages that schema drift, right? So we don't actually need to modify this data. It does a lot of really sort of efficient operations. If we do something like a rename operation, again, I don't need to go and open up the existing parquets, all it does is underneath it says, it just keeps the metadata that says, this thing that used to be called column 1 is now called column 2, right? So it's got that full tracking without actually having to modify the data. So these metadata operations actually become really, really quick. The one thing is if we go back to that idea of a delete, if I actually deleted all my data, okay, I wouldn't actually write another Parquet file. All I would do is delete all of the data. But how often are we really deleting all the data from our lake? Hopefully not very often. I mean, it's something that you might be doing. Probably not all that efficient. Okay. Any questions on that?
No. Not yet, Michael.
Okay, cool. All right. So now we spoke about this thing generating a whole bunch of files. In fact, let's just practically go through that first. Okay, so I'm going to pop in and I'm going to show you how this all happens. Now, I'm using Microsoft Fabric. It is an implementation of Spark, exactly like Databricks, exactly like raw Spark. Okay, so you use your tool of choice. It just comes with a couple of cool, handy features, including this sort of browser, this OneLake browser. So I'm going to quickly go and just refresh, and inside of my table section, I have no tables. You can see that product that I've just deleted is now gone. And I'm going to go and create that table exactly like I did. So if I go and run that operation, it's going to go and create that. It's going to go and create a table in that storage account. So if I come back here, just don't see, it's just a weird, you keep having to go up to the parent and saying sync from OneLake. That should create a, sorry, I've got to give it a second. Spark does take a second or two just to get operations done. Okay. And this is really why I'm saying that it's not really meant for high-speed transactional operations, because everything, again, this is just starting the session up. And the session usually starts a lot quicker than that. But yeah, so anyway, so 30 seconds later, I have this idea of a table. I can go back to that table. I'm going to go and refresh. And if I come in here, I should see a product table. And inside of that product table, I have exactly what I've got. No data. I've got a Delta log, and I can go in and have a look at that thing. And we won't open it up. In fact, I say that, but yeah, let's just go and open it up, and we can see exactly what's in there. All right, so we can see that transactional record, exactly what I was speaking about. We can see the create table statement. We can see a whole bunch of other important information that I stripped out, and it's probably useful to have a look at some of them, right? So timestamp, so we know when we created it. We've got some sort of operational parameters, specifically properties and partitioning by. We haven't partitioned anything. And you would definitely partition on a large system too. Actually, because one of the big things is if we think about that single big table, that if we had a worst case scenario, we had a table with 10 million records in it, and we updated one of them. Theoretically, we would take a whole copy of that 10 million records and we'd write it down again, and then we'd have 20 million records. Okay, so that wouldn't be efficient. So we'd actually want to use partitioning, so we can group these things into logical structures, perhaps by business unit, perhaps by date, whatever works in your use case, and then we'd be modifying files less frequently. And what we tried to do is try and get a partitioning strategy that modified data within the same partition. Okay, so if we knew that we only ever updated yesterday's data, then a good partitioning strategy might be by date. Okay, because then we know that we'd actually only ever hit a single partition and rewrite that, versus if you'd partition by product or geography or something like that, you probably have to rewrite every one of those partitions every day. It would be an inefficient process. Okay, but this isn't about sort of Spark sort of optimization. We got some information about just about Spark engine that created it, but then we get to this protocol, and this protocol is really important because this tells Delta what it can and cannot do. So you can see we've got a min reader and a min writer version. So the min reader just defines the level. So when we got Spark or when we started using Delta, sort of about 2 years ago, it was on the lowest version, and it could really only support these CRUD operations. But it's really moved a lot to support additional functionality. But what we were trying to do is make this thing as backward compatible as possible. So whenever you create a file, even if the Spark version that created it is the latest version, it always creates the minimum supportable version, so that if some other process that wasn't using the latest version of Spark was running, it could work on the file as well. So in order to operate on it, any Spark any sort of instance, because remember, Spark can write on it, and then maybe we could do something with some Scala application, and then head it over to Fink, and it could do something, right? So we can have multiple applications running in it. So as long as they all supported that minimum version, we could all attach to the same file. Okay, so that's all that's important there. Okay, so just pop on back to that. So we've gone and created that table. It is empty, but it has nothing, so I can go and perform all of those little operations. So I'm going to go and run that insert. I'm going to go and run that update, and we're going to go and run that delete. And this is basically just not hiding anything behind my the magician, right? Don't have anything prepared. Okay, and that operation should finish it up. And if we come back into our lake, we should end up exactly what we saw when I described it to you a moment ago. So we've got that product. We spoke about, again, it's just being a folder. Here we can see those 3 tables and the 5 transaction logs. Okay, so yeah, so this is how Delta works. So what's really nice about it, it is an open format. And this is one of the reasons that Microsoft has chosen it for their Fabric implementation. So they have multiple engines, and all of these engines can speak to the same storage layer. So everything can work in the same place. So we eliminate that need to move data. But that's not just limited to Fabric. Obviously, we can use something like Databricks to modify this data as well. So we've got a nice use case for this sort of multi-tool support. All right, let's head on back to our slide. Okay, so maintaining data. So we can see how we're generating a lot of extra files, and these really need to be managed. And there's 4 operations that we want to look at. So the first one is describe history. So describe history says go show me what I've done. Then there's optimize. So optimize, improves the performance of a thing. And really this has to do with that small file problem we spoke about earlier. So if I do a whole bunch of little inserts with one row inserts, I probably want to sort of compress those down into a single big file. Yeah, then I've got a vacuum operation, okay, and then I've got a restore. So let's head on over back to our notebook. We'll have a look at that. So come back to our management. Okay, so we've got this idea of describe it, and again, I'm in Spark and I'm using the SQL endpoint. Now you can use sort of any language you want, but if I run this describe operation, which actually has the results here already, which you can see I ran this notebook just before, it's going to go and query the state of that file, and it's going to get all of the transactions that have happened. So if I go and just give another second or two to run. Nothing ever runs fast when you're demoing it. Okay, so we essentially got those 5 operations that we spoke about earlier. And we can see that we started off with that first transaction, which is the create table. Then we've got the write, then we've got the update, the delete, and then the sort of add column. Okay, so this makes it quite nice because we can actually go and see what happened and when. So specifically, we often get queries about Johnny accidentally did this thing and he shouldn't have done it. Can we roll back to the transaction just before that? Well, now it's very easy to see that. In SQL, we're never really able to do that. All we said is, his transaction took place at this time, so let's roll back to the point, just before that. Okay, so we can go and see this. Then we've got this optimize. Okay, so optimize, and realistically, I can't run optimize on my 4 files. There's really not enough data here to optimize. But what this is going to do is it's going to go and figure out what files can be compressed into a single file. So it's going to go and aggregate all of those those little partial records, and it's going to create a new record, but it's going to leave it there. Okay, so if I went and optimized, what would actually happen in this case is I would have these 4 records. Okay, it would, the 3 records. It would write a 4th record. Okay, so that doesn't sound very optimal because I've now created more data, but it would be the full aggregation of these 4 bits of data, so that anytime I queried it, I would get that that latest version all rolled up into a single file instead of having to read lots and lots of little small Parquet files. But how do we deal with the accumulation of all of these small files? And that's where the next operation comes in. Okay, so vacuum essentially says, I'm going to give vacuum a date. Now, by default, it comes with a window. It's 7 days, 176 hours, I believe. Okay, and what it does is it goes and removes all files that have been marked as deleted, because if you remember in our log, we actually marked files as deleted. So any file that has been deleted that's older than that sort of given date, we actually would remove from the system. So that goes and, so this is the only action that really should be able to delete data. You can, as a, we spoke about transactions that might break. What often would happen is you would write a file and then your transaction would fail and you would have to write a second file. You would be responsible for cleaning up that file yourself, but you wouldn't delete other files. So there is a bit of an honesty system happening in Delta. It is absolutely possible for a rogue library to come in and break things, right? So that's where you want to make sure that you are running on supported versions. So you don't want to let somebody who wrote their own version come and do something, right? Okay, so vacuum would then go and remove any sort of old ones, and there's a couple of options here. So what I can do is I can run this retain option, and that says, what, I actually want to set that value to something different. So I'm going to say, go and delete everything that's older than 0 hours. Now you can imagine that this thing has a problem with it. It's because if I'm deleting anything older than 0 hours, I'm actually affecting transactions that could still be running, right? Therefore, I could clean up files being run by a active transaction. So the guidance is really shouldn't be anything less than a day. I think a day for a transaction is probably still a little bit generous, but you definitely don't want to be running this in production. There is a nice little option called dry run that will actually tell you the effect of what you're about to do. So it'll tell you that we're about to delete, X many records. Now you will notice that this transaction failed, and that's because it's saying, it's really a bad idea for you to set that retain to 0 hours. But if you absolutely wanted to, there is another little option where you can go and tell it that, I actually want to, I don't want you to honor that. I want you to just do it, right? So it's not going to validate that schema, and then I can then go and run that transaction. It's not going to do anything in my case because my transactions are too small, but I am able to run that once I've enabled that check. Okay. Okay, so here we can see that we've now gone and cleaned up that path. Okay, and yeah, finally, okay, so the last thing we want to speak about was this idea of a restore. And this becomes very possible because of this thing that we have. We have this log that says, at any given point, I can tell you exactly which files were valid and which ones weren't. So if I wanted to say, go and give me, as at version 1, okay, so you'll see that we've got this idea of versions, or let's say version 2. So obviously this 0 was create table, 1 was insert, and 2 was go and update. So I wanted to see what it looked like at the point that I updated that data. Now SQL couldn't really do that. We have temporal tables that you can go and do this query, and this feature is very much like that. It's called time travel. Okay, and I can say go and query this table as it looked at this point. Now this is where you must also think about that vacuum operation. If you vacuumed up your data up to, let's say, yesterday, I can't time travel to a point before that. Okay, so it's going to be this balance of removing excess files versus my ability to time travel. And the guidance, a very thumbsucky number, obviously, admittedly from Databricks, is really a week is probably a reasonable number. Okay, so if we wanted to go and query a table, if I go and say select star from product, that's going to tell, it's going to show me exactly what the table looks like right now. So that's with all 4 transactions. Remember, I deleted the record Apple. But what I can do is I can actually come in and say, go and show me what that table would have looked like at version 2. Okay, so it's going to go and run. And okay, my vacuum did work. All right, I'm going to do this just because I don't want to So I'm just going to, because otherwise it ruins this demo. I'm going to go and just run all of those transactions. In fact, I can just go and run all of that. So what I'm doing here is I'm just going to replay all of those transactions. So we're going to get back to that state pre my vacuuming operation. But that's, I think this is a good example of how vacuuming can be a dangerous operation. So you want to be careful with it. But you also don't want to not do it, right? You absolutely need to be running daily or perhaps over the weekend. Are probably good schedules for that vacuum operation. But again, your mileage will vary. Yeah, so that should be everything. I'm going to go and run as of version 3. And I'll see that data. So version 3 was after the update was with the delete. So I've only got a single record. If I wanted to see it just for the delete, I can go and query. So this makes it very flexible. I can actually go and query any state of my table at any point of time. I don't have to do it as of version. I can also give it as of a timestamp. So if I knew that, what did it look like at lunchtime yesterday, I wouldn't have to go into the version table and find the correct version. I could actually just give it a time. Okay, but perhaps you don't just want to query it. You actually want to roll back. So management comes and says, Jimmy did that thing. We absolutely need to roll back. So I can say, restore table, and I'm going to restore the whole table back to version 2. So my whole table is now going to go roll back to version 2. It's not just the query. Okay, it's actually the whole thing. So anybody who comes in at any point in time will then be able to go and query it. So if I go and query that table as a regular user, I will see only that table. Okay, now if we come and have a look at the record, what we're going to see is what happens is it doesn't go and delete transactions, because I went to this version. So it didn't go and delete all of those guys. It actually goes and adds a 5th record, right? Or a 6th record in our case. Okay, so that is saying, go and restore, which means that it actually is possible to time travel back into the future, right? Okay, a little bit of a movie reference there. So if I knew that, I just needed to do this rollback and then I needed to get back, I could actually, go back. I need to be back at version 5, right? Oh, sorry, no, that should be that guy, not that guy. So go and restore that version, and now I'm back. Okay, so now we've sort of restored back to our initial state, and that's fantastic if you think about what's happened with SQL. There is another function I didn't discuss, and I probably should, is the idea of cloning. So what cloning does is gives us the ability to create a copy of the table, but all it does is it points to to the sort of transaction log of our first file. And there's 2 versions of cloning, really. There's shallow cloning and there's deep cloning. So a deep clone will make a full copy of the data and the transaction log records. Okay, so it creates a new table and it has a pointer back to the other table. Versus a deep clone, then a shallow clone only has a reference point to that. So you can actually, for test scenarios, if you think about, actually we want to know what our model would look like if we go and add this column, run this sort of query on it, and then do this kind of stuff. And I'd like to do that what if scenario, but I don't want to incur the cost of copying my, my 2 terabyte table across. Shallow clone could be a very efficient way of doing that, right? Okay, so cloning can be another fantastic way of managing your data. Okay, questions on any of that? All right, we can pop back to the slides. Okay, so we've got that. We spoke about those 4 sort of management options, and that's sort of and we did that sort of demo. Okay, so why Deltalake, right? So it's just sort of starting to wrap up if we think about what we've seen today. The first thing we can see is how it's scalable, because it's using this storage in the cloud, and because it's just this write forward operation, and it's got this sort of optimistic concurrency. I can actually scale to huge sizes. If anybody's worked with SQL DW, they'll know that you've only got a limited number of concurrent connections, versus this actually has sort of theoretically infinite growth. Okay, then we've got different workloads. So we've got batch and streaming. We didn't really look at streaming, but streaming in the sort of modern world is actually not true streaming, we actually start speaking about micro batches, and that's what this gives us. One of the other nice things that we get out of Delta is this ability to use Deltalake as a streaming source. So if we need to calculate deltas, that kind of thing can become very easy. It gives us scheme reinforcement, which is something we don't have in the CSV JSON world, right? And while that flexibility is sometimes useful, it's sort of that Spider-Man thing, right? With great power comes great responsibility. Without a schema, we often end up with conflicting data that often causes more problems than it actually solves. Okay, but as much as we have schema reinforcement, we also have schema evolution, right? So it's cheap to modify this data. You saw how we could add a column with zero cost to our storage layer. If you've ever done a sort of altered table on a big table, especially if you say not null with the default, you'll know that operation can sometimes take hours because it actually has to go and recalculate that entire table. And obviously, when that happens, because of the pessimistic concurrency, you actually lock the whole table. I'm sure a couple of us have been in that world, right? Again, next thing is it gives us ACID compliance, right? So we spoke about what all those ACID properties are, and we saw why they're so important. But it gives us a lot of surety about the operations that we're performing are transactionally safe and isolated from one another so that we can actually work together. Okay, and then finally, we get this idea of versioning and time travel, which allows us to sort of go and see what our table looked like in the past. It allows us to roll back and roll forward. Okay, obviously, again, just a reminder: you can't time travel back past the point that you vacuumed to. Okay, so in conclusion, Delta can absolutely solve a lot of problems. It gives us a nice abstract protocol to write to things. Looks a lot like SQL. Handles the way we have. In fact, that's the next point. It feels exactly like a relational database. So I'm doing those sort of CRUD type operations. I've got this transaction. I've got that transactional safety. I don't have to worry about sort of different schemas being written and they're causing sort of problems download. And how do I deal with schema drift and all of these things that we've always had issues with. And then management is really important because those files will grow on you and you need to run those maintenance plans. Now, a tool like Fabric does do some amount of maintenance for you, not nearly enough. So it's important that you start doing a lot of these operations yourself. Okay, so that is the end